Alright, so I think we could start. And I just wanted to show you this because we discovered only now that Georgy Voronoy was a Ukrainian, or at this time citizen of the Russian Empire, and he could be the solution to a problem that we just discussed the other day, that is to somehow create polygons based on points, and it's called Voronoy polygons, and this is a famous Ukrainian mathematician who was also on a coin recently, 2008. Maybe you saw the coin, but maybe not. But this is just an aside. Today we want to really I want to really show you the basics of spatial statistical analysis. I think I will first, first as always, I will tell you something more theoretically, and then I will show you, and then I will distribute the syntax files, and you can replicate it again step by step what I did, so that you can kind of do it in your own pace. So, okay, we start with an arrangement of features in space. That's what we usually have. We have places of living, or we have countries or other things, but it's usually they are somehow arranged in space. And now what we already did is that we calculated distances between one feature type and another feature type. You remember when we calculated the distances between respondents and the cinemas. And that's what you would probably get. You would have a list of features or observations A to E, and you would have a list of distances. And you could use this list as an independent or dependent variable in some kind of meaningful analysis. Yeah, that's more or less it, but it can be very interesting. So what we do in spatial statistics now is that we calculate the distances between features of the same kind. So here in this picture we calculate the distances from A to all the other observations, to B, to C, to D, to E, and we do this for all the observations, and what we get is a distance matrix. This distance matrix is n by n large and contains all the distances from each and every respondent to each and every respondent. Of course, the diagonal is not defined. You could also insert zeros, but because the distance from A to A is 0 or is nothing or whatever. So on this allows for the first spatial statistical analysis. I will show it to you only theoretically, because there are not so many applications in sociology, I think. But this is the analysis of distributions in space. Sometimes you could have a question that asks, yeah, well, I have some occurrences of, for example, diseases or robberies or something else, and I want to see whether this is spatially clustered, that's it's more than randomly clustered in one place. For example, robberies are usually clustered in some places, and diseases as well. And what you would do in this case is you use this distance matrix, as we had in the slide before, and you calculate all the mean distances. So you would calculate for all the observations the mean distance to all the other observations, and you would calculate the mean of that. In this example, it's 8.7 distance units, whatever that is. And you would do the same with a random allocation of the same number of observations in space. Of course, you have to do it sometimes, the computer program will do it for you. And then you can compare the observed mean distance with the mean distance that would occur when there would have been a random occurrence of the same number of occurrences in space. And then it could be that it's lower the mean. That would mean there's some kind of clustering, or it could mean that this is larger, and that would mean that it's more spread out than when it would occur in randomly. Okay, so this could be, say, the first spatial method of analysis, and you would find it in the program if you would have a question in this direction. The next method of spatial analysis is interpolation. So now I show you some methods, only that you know that these methods exist, and then I will go into detail with other methods. So interpolation can be very helpful when you have like different districts or different neighborhoods or other aerial units. And as I told you in the first day with these kind of aerial units or spatial aggregates, there are two problems. One is the scaling, there are scaling effects, and the second is that there are zoning effects. And in a lot of, or not in a lot of cases, but sometimes you just have the wrong level of aggregation for your analysis. So for example, you have information about zip codes, but you want to have cities or neighborhoods or whatever, and so it doesn't fit your level of aggregation. And one solution can be spatial interpolation, and then you can aggregate the surface again in the desired spatial units, but that's probably not something you need all the time. So what's the idea behind spatial interpolation? The idea is that you calculate a surface, and for each pixel or point of this surface you average spatially by the neighbors, the values. So when we want to calculate the black point on the upper in the upper picture, we use the information of the neighbors that are the red points in the circle to get the mean value, and then we can assign this to this black point, and that kind of smooths the whole picture. So this is kind of an analysis of density, or you could say weighted means of the surrounding areas. This is very abstract now, but I will show you in the next pictures, and you will get it immediately what, so to say, the advantages of this method of spatial interpolation. So for example, here we have the share, we have different neighborhoods in Munich, I think. It was a project of Katrin. Katrin, they did some kind of correspondence experiment where they wanted to measure discrimination on the housing market. So they sent emails to landlords with an application for a flat, and once it was a German name and once it was a Turkish name, and they looked for the answers, and I think in 10% of the cases the German got an answer and the Turk didn't got an answer, and this is kind of the rate of discrimination on this step. And they had the idea that this discrimination can somehow be related to the place where the flat is in the city. And so all the different points are these experimental units, these houses or flats, and all these aerial units are neighborhoods in Munich. And this is the share of foreigners in city districts or neighborhoods is encoded in the different colors. So the darker the color is, the more foreigners are living in this area. So I won't go, I don't know the results. I think there was no correlation, but it doesn't matter. It's just to make the point. So what can be problematic when you just calculate correlations between discrimination or the response rate and the share of foreigners? Of course, problematic can be that you have a lot of flats that are right on the border of the neighborhoods. So it can be pretty far-fetched to say, okay, this landlord discriminates because there's a very high share of foreigners, because like 20 meters to the right-hand side of the city there's a very different share of foreigners. So what you can do is this kind of interpolation, and this kind of interpolation somehow gets rid of these fixed borders but smooths the surface. So, and that's kind of the result, is that now, because all the points that are here are not the original value but a weighted average of all the surroundings, you get rid of the fixed borders, but you somehow include information of the neighboring polygons. And that can somehow be, of course, better information, because it somehow reflects more what probably the landlord thinks. He does not think in the neighborhoods, but he thinks in the surroundings of this flat, and this would be the result. And but of course you have to answer a lot of questions and you interpolate. One is how far you go with the information, how large is the surrounding information that you take into account. And so when you do this like very narrowly, you get something like this, but when you do it more widely, then you get it even more smoothed out. And you can imagine in the extreme case, when you take like the whole city into account, then you get the mean value of the share of foreigners for the game. So you get the same color for the whole city. So this is kind of something you have to adjust for, and probably something you have to have some tests of robustness, that you have different specifications and you probably look for different correlations, and maybe it's even substantially interesting, because you could say, okay, there's this correlation between this feature and this other feature on a very narrow definition of neighborhood, or there's this correlation on a very wide definition of neighborhood. And that would mean something like substantially. In this case, it would mean in the one case the landlord takes into account a very small area when he decides whether to discriminate or not to discriminate, or he takes into account a wider area when he thinks of discriminating. And this can very well be interesting. I don't know, as I told you, I don't know what was the result of this analysis. Okay, so this is the second method of spatial analysis that I wanted to show you. A third method of analysis that we also did is that we measured residential, or we were interested in residential segregation. And maybe you know the most famous measurement of residential segregation, or segregation in general. You can also calculate segregation on occupations and so on, but this is residential segregation, and it's the index of dissimilarity, or Duncan's D, and this is the extent to which within a given geographical area, for example a city, individuals belonging to different social groups live in neighborhoods characterized by different social compositions. So one interpretation of this index is, so it's an index between 0 and 1, and the interpretation would be the share of one group that had to relocate in order to achieve even distribution. So you usually have two groups. For example, in our case it was Germans and Swiss. And so when we'd have a segregation index of 0.5, that would mean like 50% of all Germans had to move to a different area so that we'd have an even distribution about the whole city. So now the problem is, so there are some problems with these kinds of indices. These are neighborhoods and they have different shares, and we calculate one value for the whole city. And yeah, then that's it. But it depends a lot on what are the kind of spatial units you have. Again, when you have very large units, the segregation index should be lower, because when you have only one city, then of course no one had to move, because everyone lives anyways in one area. Okay, and one solution to this is to use spatial indices of segregation, and this is the literature where you could find it, Reardon and O'Sullivan, and the idea behind this, there's the formula if you want to, but the idea in this is that you calculate, that you don't use like the neighborhoods or districts that you have, but you use for each and every individual neighborhoods. So I try to illustrate this with this picture. So you see all the circles are individual neighborhoods of people living in this city. And you can also vary the size of this neighborhood, of course. So to get a different, as we had the interpolation, you can vary this, and maybe you can even ask substantial questions. And you get different results. So when we had this aspatial traditional Duncan-Stee segregation index, we had a value of 0.24, which would mean 24% of Germans in this city had to relocate to get an even distribution. And we looked at different points in time, so it didn't change much between 1990, 2000 and 2010. And then we had these individual neighborhoods to see whether, because segregation can be at very different scales. So, for example, in the US, there's sometimes there's whole neighborhoods that are racially segregated. So there are blacks in one neighborhood and only whites in the other neighborhood and Latinos in the other neighborhood. But it could also be that the segregation in the neighborhood is, so a neighborhood is pretty mixed, but in one housing, in one block, that's segregated. So one neighborhood is mixed, but one block of houses is only black, one block of houses is only white, one is only Latino. So this would be a different scale of residential segregation. And we tried to look at this, and we saw that with the 50 meters radius, so very small neighborhoods, there's quite high residential segregation, and when we enlarge this, then it gets lower, the segregation index. And this is pretty similar because these neighborhoods are roughly 200 or 400 meter in diameter, so this is more or less a replication of this, and this is the variation of this. And that's something you probably could do, but you have to have good data. So you have to have, in this case we had the location of each resident, and you rarely have this kind of precise data. But probably for other questions you can use this kind of spatial segregation indices. Okay, so these were 3 different methods that I wanted to show you, but we put aside this now. And we we lay the foundations for spatial regressions now. Okay, remember these distances between units of observation, these distance metrics. And this is like the foundation for everything. So spatial analysis account for the relative position of all units with regard to all other units of observation. That is the basis of all statistical methods. Spatial statistical methods is a distance or adjacency matrix. Adjacency matrix, I will go into, I have it here. So we construct on this basis of this distance or adjacency matrix, we can construct a spatial weights matrix. So I will show you. And we do this on the basis of shared borders, which would result in a contiguity or adjacency matrix. So when we have polygons and they have shared borders, then we have shared border, or we don't have a shared border, so we can assume influence or not influence. So for example, if we are interested, I don't know, in this democratization processes like in political science, we can use distances, we can use nearest neighbors, or we can even use some kind of other network data. So for example, with countries, they use often not like the distance between countries, but the import and export figures. So something that has not really to do with distance, but you can use it and run the same analysis. So for example, with your networks, you could probably not use like the distance on a road network, but the assumed time of travel or something like this.
The cost of travel.
Or the cost of travel, yeah.
I have
Something like that. And you can insert it in your, you can construct a distance matrix out of this and use the distance matrix to have a spatial weights matrix.
Mm-hmm.
The spatial weights then represent the distance, however you measure the distance between two units. We assume that larger weights represent stronger correlation or influence of each other, or they represent a common context. What spatial weights you use, like you use the cost or the direct distance or the time, that's something you have to have some theory on. That's something there's no, that depends on the case and the research question, I think. Okay, now I show you just how it's done. It's really easy. So, for example, we start with the contiguity matrix or adjacency matrix. These are different neighborhoods, neighborhood A, B, C, D, and E, and they share borders with some neighborhoods and they don't share borders with other neighborhoods. And this is just reflected in this contiguity matrix. So neighborhood A and neighborhood B share a border, so that would mean the 1, but neighborhood A does not share a border with C, D, and E, and so on and so forth. So this is what we had before in the distance matrix. So and now we translate this to a spatial weights matrix. Usually these spatial weights matrices are row standardized, and this has like substantial reasons that they say, okay, the influence on one observation is fixed to 1. So when they have only one neighbor, then the influence of this one neighbor is very large. But when they have 5 neighbors, then the influence is only 1 divided through 5, so 20%. And it has also computational reasons. So, but I don't know. I can't really tell you about this. So, because between A and B there is only one shared border, the spatial weight is 1, and because between B and A, C, D, and E, so there are 4 shared borders for neighborhood B, so the spatial weight is 25%, 0.25, and so on. So see this. This is for the contiguity matrix. And the exactly same you can do for distance matrix, and you get inverse distance weight. That means the larger the distance, the smaller the weight of this one pair of observations. So yeah, we have here distances 2, 3, 10, and 7. Then we would have spatial weights of half, 1/3, 1/10, 1/7, and so on. So this is just what we get as a spatial weights matrix then. And of course you don't have to do it by hand, but we have the computer to help us with this task, because otherwise we'd be very prone to error, I think. Yeah, this is what I told you. There is only so much influence. Therefore, we standardize the spatial weights to 1, and we do it also for computation reasons. So this 1/2, 1/3, 1/10, 1/7, and so on is a non-standardized spatial weights matrix, and in the next step we have to standardize it to 1, that all the weights in all the rows add to 1. And of course the computer will do this for you, but I wanted to show you all the steps so that you can follow it and you know what the computer is doing. Alright, so this on the right hand side, this is now the basis for all these statistical methods. And I hope you somehow got how I got there. But you will have the slides so you can have a look again and try to calculate it by hand or something. I think for this kind of matrices and so on, it's always good to calculate it once by hand, and then you know how it's done, and then you can give everything to the computer. Okay, so and now the next method of spatial analysis. What can we do now with this spatial weights matrix? We can, for example, calculate spatial autocorrelation. And spatial autocorrelation is the question whether observations that are spatially close to each other are somehow more similar than observations who are not so close to each other. So for example, if here observations A, B and C are spatially very close to each other, and E and D are a bit farther off. So and A, B, C, D, E have some characteristics. So some kind of value. A has the value of 4, B also 4, C has the value of 5, D has the value of 9, and E has the value of 2. So, and just by looking on it, you would say, okay, these spatially close units A, B, C have very similar values, 4, 4, and 5, and the more distant values E and D have values 9 and 2, they are quite different. So, but of course, and when you have more than 5 observations, you have to have some kind of statistical measurement. And here the spatial distance matrix comes into play, and we just we calculate for each and every observations. We calculate based on the spatial weights matrix the mean of the neighbors. So for you see where this comes from. Unit A has the value 4, and the spatial weighted mean of the neighbors would be 4.6, and this comes by neighbor B has a weight of 0.5 and has the value of 4. Neighbor C has the weight of 0.3 and has the value of 5. Neighbor D has the weight of 0.1 and has the value of 9, and so on and so forth. Yeah? And then you get the spatial weighted mean of the neighbors, and this you calculate for each and every observation. And then in a way, it's not so simple computationally, but you can think of it as that you just run a correlation between the value and the spatially weighted mean values of the neighbors. And when there is a correlation, a positive correlation, and that's very strong, then you say, okay, we have spatial autocorrelation. Spatial autocorrelation means the neighbors are close, are more correlated or more similar than the non-neighbors. You can also have this in matrix notation. What you usually just do is you calculate the correlations of these values. You look whether it's significant or statistically significant or not. And then usually it should be positive. There are very many cases, and I know of no example where there should be negative spatial autocorrelation. That would mean that neighbors are more dissimilar than observations who are further apart. So it's very hard to construct an example in that field. But what, for example, is an example is the share of voters in voting districts. This is kind of a classical example. And you always get like this kind of small scatter plots. Yeah? And so you have different voting districts, and usually the neighboring voting districts have similar results that has different reasons. For example, infrastructure or population or politicians that kind of affect different voting districts that are more neighboring. And this is something you can then plot and calculate. So the Social Democratic Party in Germany, there's a very strong spatial autocorrelation. So when there's the value of 0.2, like 20% share of voters, then there's a lot of neighbors. In a lot of cases, the neighbors have also a share of 20%. And when the share is larger, like 40%, then the weighted average is also 40%. And this is also called, like this spatially weighted average, it's also called the spatial lag. And with the when you say lag, then you know that we are in the domain of econometrics, and it's very similar to time lag. It's basically the same. Yeah, that's. I mean, this is the global Moran's I. It's called Moran's I, this correlation, and this is the most important or most widely used measurement of global autocorrelation. Global means you get one value for this one characteristics for the whole area, and there are also local measurements. I won't go into detail, just that you know. Sometimes it's handy to have a global measurement, but it can of course obscure the view on some important processes that happen in some parts of the country or the city or something, so that the correlation is strong in one part of the city and not so strong in the other part of the city, or there are like dividing lines or something else, and you wouldn't capture this with the global Moran's I. So when you are really interested in these spatial correlations and autocorrelations, then you can read further on with the local Moran's I and so on. So it's all very good explained in this book that I gave you. Maybe
we already scanned.
We already scanned, yeah. So we can maybe distribute it, and
yeah, it needs some time to perform after scanning, because it's
to prepare the PDF.
Okay, yeah, but later on or something. So this is something you can go more into detail when you have the book. All right, and now I will show you how this is done with the Data program. So you can't, you just have to watch what I'm doing. You can't, at the moment you can't replicate it. So I have now this data syntax, and I will go line by line and explain you what I'm doing, and then you can do it on your own. So the first, so you see in the syntax we always have like commands, and we have some comments like in a lot of programming languages. So, and because the syntax window tries to help you and to get an overview, the comments are always in green, and they are not like used by the program, so the program will ignore the comments. But it probably doesn't matter so much. So you start with the command clear, which will wipe everything off your current session, and that's always a good thing to do in the beginning. And then we need to change the folder to where you stored the data, because you don't have any data yet, because I give you afterwards. You cannot do anything, but I just gave this, like my data folder is on the desktop, and it's called Kiev, and it's called Data. So I will run this first, and you see in the results window it's just doing what like repeating the commands that I had here in the syntax file. So the first thing I just want to show you, because that's probably something you can do something with further on, is you can also import shapefiles in Data and display them. So this is the command shape to DTA. DTA is the data format, and we do this, and you see it ran the command, but it didn't, like, you don't see anything. Yeah, maybe I increase the font. Like this. Okay, and but what it did is, so if you are interested, you have here the website where you have all the documentation for this command. But what it did, and that's something that I wanted to show you, because it shows you more how shapefiles are built. Yeah? We now kind of imported this shapefile, and we generated two data sets, and one is a data set of the attributes, and this is just, you might remember here on the right, this is just the fields that we had before, like neighborhoods, and we have inhabitants, we have Germans, we have foreigners, and we have the share of foreigners. That's something that we exactly had in our QGIS program. So we have different columns, and we have different characteristics and so on. More interesting probably for you to understand the concept of the shapefiles is the other data set that was generated. I call it neighborhoods, neighborhood coordinates, and this consists only of the coordinates of the neighborhoods. Now, neighborhoods are no locations, no points, but are polygons. But what's now in here is all the points that make up one polygon. So this is neighborhood 1, and it's made up of a lot of different points. Up till like 100, 200, okay, it's made up of 257 points. And these points in turn can be used to paint the neighborhood. So now we have like 5,609 points that make up all the polygons that we had in this shape file. This is just something I wanted to show you because I think it makes very clear how all this concept of shapefiles and polygons work. And we can use it to... No, it's not working, of course. Okay, now you can use it to make some easy graphs of what you already had. That's something you can also do in R, and it's probably, if you have like your shapefiles ready, your polygons, and you have your data, then you don't even have to use the geographic information system. But as soon as you want to delete some neighborhoods or want to adjust them or want to merge them or do something with them, then you need a geographic information system. But yeah, it's also because then it's like in the same scheme as your other graphs that you do with your statistic analysis. Sometimes it's nice to have, and I think a nice way of illustrating your spatial data is to use small multiples. That would mean you use this picture like 4 times, but with different characteristics, with different coloring, and then you have a 2 by 2 matrix, and you can display a lot of information in a very small space. That's usually very nice. And that's something, of course, you can do more easily with data in R, and it's not so nice with the geographic information system. Yeah. All right. So that's something I wanted to show you, and when you're interested in it, then there's the corresponding website. Okay. Now we go to our spatial weights matrices and spatial autocorrelation and so on. And I prepared a data file for you, which is called knend.csv. CSV is what you get when you export your data from your geographic information system. And KN stands for constants, and IND stands for individual. So this is just a shortcut, which probably confuses more than it helps. Yeah. Okay, first command is I import this data, and everything was fine, and I have now here all the different variables that are part of this CSV file. And all right, first what we do usually is we look at the data. We look at what's inside this data, and the first thing we can do is to use a scatter plot to see whether the spatial everything was correct. And first we can use latitude and longitude, and the scatter plot looks a lot like, so these are the different observations with the coordinates, and that looks a lot like the respondents that we had in our geographic information system. So that would show me that there were no huge mistakes in exporting the data and importing it again, and as you might know, with importing and exporting there can be a lot of problems. And we see here latitude and longitude. As I told you, this is unprojected. So this is not in meters and kilometers, but this is like degrees and on a globe. And so for our statistical analysis, of course, we need a 2-dimensional space, and therefore I've also included y and x, which are the projected coordinates. But when I do a scatter plot of this it looks more or less the same. It's a bit more stretched out, but the proportions and so are all the same. And we see here now we have like, I think it's meters, like 512,000 meters, maybe, I don't know, south of Berlin or something, I don't know. No, it's not,
It's a different measuring.
it's a different measure, but you could, from this measure, you could infer where the 0 point is in Germany, but I can't now, from the back of my head, I have to think about it. Okay, the next thing we can do is to have a look at the variables that we have in this data. And you see I commented for you what it means. Sat NH means satisfaction with the neighborhood where the people are living. And I already told you yesterday one command would be the summarize or short sum command. And when I run this, no, this is not so nice. I run it again. I run it and I see for this dependent variable I have 685 observations with a mean of 7.79. It's a scale from 0 to 10, min and max. And there are some standard deviation and so on. I can do the same for age. All the respondents gave us their age. So I have again 685 observations with a mean of 45 years, which is in constants pretty accurate. So you see Germans are pretty old, like the population of Germany is pretty old. Despite the fact that in Constance there are a lot of students, but also there are a lot of people coming to Constance for retirement because it's nice at the lake, and so rich people come to Constance to retire, and this offsets the effect of the students a bit. So we have responded, and of course we have no respondents under the age of 17, of course, so the real number would be a bit lower, maybe 40 years old, but still it's quite high, I think. So we have respondents from 17 years old to 93 years old. Okay, and we can do this for some other. I show you the two spatial measurements. One is called Zentrum 100. This is the distance from the individuals to the city center in 100 meters. So when it's 4,000, then I divided it through 100, so it's 40. And when we look at this, we see it's again 685 observations. The mean is 6.3. That means the respondents are 630 meters away from the center on average. There's a min and a max, and we see everything works out more or less fine.
Maximum means that not more than 1.6 kilometers out of center.
Yeah. There are, I mean, of course, Constance is larger than 1.6 kilometers, but there are some smaller centers that provide for postal office and shopping, and even there's some kind of office from the city where you can pay your taxes and do everything else. So there, of course, you could say we use only one center, but this is something you have to define theoretically. So for this purpose, the center was defined by like the possibility to do the shopping, to go to school, and so on. And so there are some centers. Okay, and finally, we have the proportion of migrants in the different neighborhoods, and for 685 observations, and the mean is 0.13, which is 13% is the mean proportion of migrants. Not exactly, but not exactly for the whole city, but for the sample that we have now. So the surroundings of the sample. So it's a bit more complicated. But what is important here is that I have the same number of observations everywhere. So missing values are really a problem for this kind of analysis, because when you have distance matrices, you can't have empty fields, and this would be problematic. So you have to prepare your data in a way that you have no missing values, and you can do this by some kind of substitution or insert some values, or you just delete them. And I think that depends also on your theory and the number of missing, number of missing values and so on. When you lose half your sample, you should probably think of some kind of imputation methods. When it's only, like in my case, it was about 10 observations, so I just deleted them. Okay, now the first thing that we can do just to look at the data is to run a normal linear regression. In Stata, this is a very simple command. You have the command regress or short rec, and then it follows the dependent variable, and then it follows all the independent variables, and you're good to go. So and when you do this, you get a picture like this, which is the linear regression. And what would you say? Disappointing. There's a negative effect of the proportion of migrants on the satisfaction with the neighborhood. So when you live in or when our respondents live in a neighborhood where there are a lot of migrants, then they are not as satisfied with the neighborhood compared to when they would be living in a neighborhood with less migrants. And females are usually more satisfied with the neighborhood than male. Probably, yeah, I don't know. It can be because they are usually satisfied with everything or not. I don't know. It's just speculation. So it's just a control variable. I have no hypothesis on this. I would have liked, of course, that they are more satisfied with their living conditions when they would have been closer to the center. But you could also make some arguments that it's nicer more outside of the city, because there's usually a lot more green or something. So when this would not be like an example, but we would really try to model this appropriately, we could probably include some kind of squared term or use it categorically, that we say, okay, people are more satisfied when they live right in the center, or when they live right outside, but not so much in the middle. I don't know. You could have a lot of thoughts about this, but this is just as an example, because I know that there is spatial autocorrelation, and that's something I want to show you. Okay, what we do now is we calculate the spatial weights matrix and the Moran's I. And because this is computationally intensive, and I want to show it to you, and I can show you a matrix of 1000 by 1000, we keep only the first 15 observations. Keep 1, 2, 15. So now we delete 670 observations. This is just for illustrative purposes. Later on we will run it for the whole sample, but then I can't show you. And now I have two specifications for spatial weights matrix. As I told you yesterday, the SpatWmat command stands for spatial weights matrix. And you have to tell the program, of course, a little bit on what you want to do. You have to tell it what name shall the matrix have, what are the coordinates, x and y coordinate, in what kind of surrounding shall the program look for. So this is 800 meters, because when it looks like it gets zeros for more distant observation. And then this is the interesting thing. We could have either a binary matrix that they are neighbors or they are not neighbors, or we can have, when we don't specify this, we can have like, this is just distance matrix, but this is a row standardized distance matrix. And when I calculate this it goes really quick, because it's just a 15 by 15 matrix, and we see here the result dimensions is 15 by 15. The median distance is 601, and there are some other distances and so on, and I will show you the matrix now. And so we gave the names WB for binary and W, and now we can just, with the command matrix list, and then we give the name, we can just have a look at these matrices, and WB would mean it's the binary matrix, and this is what we would expect. So the 1 stands for they are neighbors, the 0 stands for they are no neighbors, and it's non-standardized. And when we have a look at the other matrix, okay, it doesn't fit on one window. Maybe I can make it a bit smaller. No, I can't. But you see, this is also like, but here are 15 different, like, this should be longer, the matrix. But you see here, observation, I think 2. This observation has 0.03 weight of 0.03. It's very low, 0.08, 0.03, 0.1. This is already larger, and this is probably the closest neighbor and has a value of 0.44, which is because it's standardized to 1, it adds up to 1. It's quite a big influence, very influential neighbor, so to say. So every row would sum up to 1, and you get all the different values.
It's like transition matrix in Markov and chain, the same principle of building.
Yeah. I don't know much about Markov chains, but I can tell you that that Voronoi was a PhD student of Markov. So everything is connected to everything.
Nearest neighbor.
Nearest neighbor, yeah. You can also calculate distances by maybe in science, yeah. Who is a student of whom? That would be probably interesting as well. Okay, now easily, when we have this spatial weights matrix, we can calculate the Moran's I, and this is done with the SPAT GSA command. I don't know what GSA stands for, but it would allow a lot of different measurements for spatial autocorrelation. Yeah. SA stands for spatial autocorrelation, I would say. And after this command, you give all the variables that you are interested in. This is, in my case, all the variables I have in the data set. You tell the program what kind of spatial weights matrix you want to use. This is the standardized one that I used. And you say, okay, I'm only interested in the Moran's I. And when we run this, then we get a window where we have all the Moran's eyes, all the Moran's eyes, and we see statistically significant are the two values that are that should be spatially autocorrelated, because two neighbors are more or less the same distance from the center and live in an area with the same proportion of migrants, of course. But this is only like for these 15 observations that we have. So it could be in our data set, it could be very, very different. So, for example, the satisfaction with the neighborhood, there should be some kind of spatial autocorrelation. If there wouldn't be, then I would be suspicious of my data. So, but this is how you calculate this this Moran's eye, and then you're good to go. So it's not so complicated. Okay. Now it's almost 12. I would think that we make a short break. And I distribute to you the syntax and the data.